Anyway, so thanks everybody for joining me today. So my name is Jody Medich, and I have a couple different hats. I am an artist. I am first and foremost. That's the thing to keep in mind about me, and it shows up in the way that I do all of my work, because I tend to question established norms and challenge them to imagine what else is possible. So my special area is human-machine interface, and I am currently the principal design researcher for the CTO of Microsoft, Kevin Scott. I'm also the CEO of a company called Superhuman-X. It's a startup that I founded to create superhuman interface. So I talk a lot about how I make superhumans, not supercomputers, and we'll get into that a little bit more in just a second. And then I'm also a practicing artist, so I paint and do big, huge metal sculptures, and recently was shown in the Smithsonian in the US, which is a really big museum in Washington, D.C., with lots of different venues, but our piece was in the Smithsonian for a few months, right across the street from Mr. Right, I'm not going to be political. Anyways, so I also have roots to Austria, just so you know. My grandmother is Austrian. Her last name is Potapatic. They grew up, my family is from the border of Austria and Hungary. So we have a lot of Austrian traditions that we do, and I love Austrian pastries, as well as beef soup. Okay. So that's a little bit about me. And there is going to be a lot of adventure here. So I have prepared a talk that was about 45 minutes. Now, it took us about 14 minutes, though, to get into the Q&A. So I want to, and I was going to leave 15 minutes at the end, but we've just kind of lost the 15 minutes at the end, I think, right, Nikki? Yeah, I thought so. All right, so what we're going to do is that I'm going to start on this journey. Now, it's pretty dense content. We have options. If in the middle of it, you're like, wait, since there's only a small handful of us, we can have a conversation at any point, but keep in mind that means we're definitely not going to get to the end of all this content. However, I think that the conversation might be more beneficial as opposed to you just sitting there listening to me deliver content. What I would recommend, though, is for me to get through these, I'll kind of, yeah, so let's just dive in. Please chime in with questions so we can diverge this more into a conversation instead of a lecture format. I'm totally good with that. But if there are none and you're just really interested in what I'm saying, then I'll just keep rambling on until somebody interrupts me. Sound good?
Perfect.
All right, we're all in agreement. You're gonna have to speak up though, because I will not be able to see the chat, but Laura will, and she can always alert me if there's something going on that I need to know about. All right, so let me share my screen. Okay. Oh, not that part. Nope, not that part either. Ta-da! Can you see that now? Yeah, okay. So I'm going to give you this talk as from the perspective of the CEO of Superhuman-X, because I may see things that my current employer may not approve of or agree with or condone. So this is not the words of Microsoft. This is the words of Jody as CEO of Superhuman-X. So are we all in agreement? Yes, cool. All right. So first things you need to know is that, tech is exponential. And what we mean by that is that tech has been showing for a long time this doubling of performance for as the price drops. So every year we see a doubling of the compute power, while the cost and size of that compute power decreases in a relative way. And so what that means is that every year we see a doubling of what's possible. And for a long time, we thought that was limited to something called Moore's Law. Are you familiar with Moore's Law? So Moore's Law was coined by Gordon Moore, who is the co-founder of Intel back in the 60s. And he noticed that the This is specifically about the transistor, that the size of transistor shrunk while the compute power of that transistor doubled. Now, we are seeing the slowing of Moore's law, meaning it's coming to an end. And people are starting to panic and thinking, okay, well, that's the end. No more compute. This is not going to continue this exponential. But Ray Kurzweil from Singularity University and one of the directors of engineering for Google, he says that Moore's law is really only a portion of the exponential pace, and it refers to this paradigm here called the transistor. It's only a portion of that exponential pace, and that in fact there's multiple paradigms of compute that sort of build on where the last paradigm left off and accelerate that curve even faster. What that means is that today we're hurtling towards a new paradigm in computing called cognitive computing. It's also called automation. It's called AI. We don't have a specific term for it because it's still in that sort of about to disrupt kind of state of compute. So it's in that early stages of the paradigm. But even still, when we look at it, we are going to see that 3 in 5 jobs are about to be automated. At least that's according to the World Economic Forum, right? They see that the fourth industrial revolution, as coined by the German government, which refers to this automation or cognitive compute, is going to lead to this massive disruption on par with the first industrial revolution. That's how big of a disruption it will be to our societal structures. And for better or worse, right? And one of the biggest things they talk about is that nearly 60% of the workforce will find the majority of their tasks automated. And this is not just for blue collar workers, as the machine revolution caused. Instead, it's going to be knowledge workers, people with specialized knowledge, such as doctors and lawyers and all that kind of good stuff. Now, I'd like to pause here for dramatic effect, because most people start to panic when I tell them that 60% of jobs are going to be replaced. They start thinking, oh my God, this is ridiculous. What are people going to do? We're just going to turn into couch potatoes. AIs and robotics are going to do everything, and then they're going to come kill us, and we're going to all die. Come on now. You've seen too many movies. The only job lost to computer automation since the advent of modern compute in the 50s, is an elevator operator. It's the only job that's actually been lost. In fact, in previous periods of rapid technological change, we've seen the rise of new sectors and new employment opportunities that never existed before. And the machines just help us to achieve more tasks than we could prior to that machine, right? It's just, for example, machines amplified our physical output dramatically. So much so that you might say that humans are exponential. Now, I get a lot of trouble for this because it's not technically, mathematically, an exponential. Okay, we all agree on that. However, humans are developing more and more things every year, achieving things that we never thought were possible. We're seeing disruptions happen over and over again. Fortune 500 companies are disappearing while new ones are being invented. It's impressive how much humans are accomplishing. And we tend to focus in these tech talks about how compute is going to take over the world. But we need to understand that compute is in service of humans. It's not a replacement for humans, it's an augmentation of human capabilities. Extreme sports are an awesome example of how humans leverage tools to do unbelievable feats that we never thought were possible. I highly recommend reading this book, even if you're not into like interface. This is The Rise of Superman by Stephen Kotler. And in it, he talks a lot about how humans leverage things like flow state to accomplish tasks that we never thought of before. And he uses extreme sports as a metaphor throughout the book. It's really interesting. Now, in it, he talks about the fact that extreme sports are really shocking to human beings because they do crazy stuff we never thought was possible. And when there's two ways that people do this. One is that me as an extreme athlete, I see another extreme athlete do some trick that nobody's ever attempted before, and they land it successfully, and everybody is amazed. And that sparks in my brain, oh, wait, if that's possible, I could do this, right? And so what happens is that we see that initial idea, and then we build on it, and then somebody sees that, and they build on that, and then they build on that, and then they build on that. So it's like a monkey see, monkey do better type of situation. In addition, we have something called the kicker in extreme sports. Now, the kicker is the launch pad to do things that we never thought were possible, and they change the game. In English, when you play poker, the kicker is the card that changes the entire hand. So in the same way, in sports, the kicker is the thing that launches you off to do crazy things. Right? And so the kicker can come in the form of a simple ergonomic change. It doesn't even have to be a new introduction. It could just be a change to the existing tool set. Take, for example, speed skating. So speed skating as an Olympic sport was around from 1979 to started in 1979. And it took us 19 years of Olympic competition to shave 2 seconds off the world record. Suddenly, in 1996, the Olympic board accepted something called a clap skate into this competition. And I don't know if any of you were alive back then, but I remember this very clearly. It was this huge controversy. And the big difference is right here where the back of the skate is not actually attached. Instead, it is only attached in the front with a hinge. And when the skater pushes off, what happens is the blade stays on the ice so much longer because it doesn't have to move with the leg of when the skater has to move their leg, it can stay on the ice and sustain the blade, which provides more power. Now, that simple ergonomic change took 2 seconds off the world record in just 2 years. So it took 20 years to achieve this, to take 2 seconds off prior. And then this simple little ergonomic change improved that with 2 seconds. And in those 2 years, the world record was broken 4 separate times. And they continue to get broken over and over again as these ergonomic changes happen. So all that it takes to amplify the human performance within a system is a change to the ergonomics, which amplify the output of that person in the system to create more efficiency. So with the less amount of effort from the human, amplified output comes out the back. And it's just a simple ergonomic change that makes that happen. Now, when we look at technology, the ergonomics of technology are terrible. They're just terrible. And if you've seen any of my talks, you're pretty familiar with my exposure of GPS, which GPS is, a great tool, but you have to pay so much attention to it. And you can easily get lost if you're using this map. A lot of times you're having to orient yourself. You're walking up and down the street trying to figure out how this map relates to the environment that you're in. Now, usually you're doing it while you're doing some other tasks that you should really be focused on. You shouldn't be focused on the map. You should be focused on walking or driving or whatever task you're trying to do. But in this instance, when you're using technology, you're doing 2 tasks, not 1, but 2 tasks. You're managing the phone and the map, and you're also doing the driving or or walking or whatever real world task. And that's not just limited to mapping, right? This is any sort of task. You might be, say, trying to copy and paste content from one application into another application. And so in order to do that, you have to manage the task of the compute as well as the task of copy and paste. So you're never just doing one task. You're always doing multitasking when you're trying to use compute to complete some task. And unfortunately, humans we're terrible at it. We can do maybe 2 at a time of high focused tasks. Fighter pilots can do 4, but they're considered especially gifted and they have to train to improve that ability significantly. Now, the problem is that we have short-term memory is in limited supply. And the short-term memory is the thing that keeps track of all the information in a given context. If you switch contexts, you lose all that information. Okay, it's called the doorway effect for a reason. The short-term memory is purposely easily interrupted. The idea is that it keeps track of all the information in a given context, and if you switch, it drops all that out. Okay, and so it doesn't matter if you're literally walking into a new room or switching between your phone and the real world or moving across a browser tab, whatever. Any one of these things are considered a doorway, and and that interruption can cost you anywhere from 0.3 seconds to 30 minutes to get back to whatever task you are trying to achieve. This type of interruption adds up significantly over time, but we've become kind of nose blind to it. We don't notice it happening because we're just so familiar with it now as a cost of using our compute devices. But to give you an idea of how bad this becomes, you check your phone about 2,600 times a day. That's 2,600 times a day that you're like checking to see, was that a phantom buzz? Was that a real buzz? What time is it? Do I have any new messages? Whatever. All of these things require cause a disruption in your thought process. Now, we have an opportunity to fix this thanks to cognitive computing. Because when we look back through time, each paradigm of computing has come with a new set of HMI that is geared to help people to achieve the tasks of the tasks made possible by that compute platform. For example, the mainframe, the point behind the mainframe is to encode data. So the main human task that people had to do was to encode data. Then this PC, which we're mostly familiar with, was about operating software. PCs are designed to allow the human being to operate different software. So the human-machine interface is specially geared for that. In cognitive compute, what we see is that the task that humans will need to do on this platform is to collaborate with AI. So we're augmenting human cognition on this platform. Now, here's how those HMIs looked. So in this, from 1899 to 1970, we had the mainframe computer and we encoded data. That's when we used something called a punch card, which was basically a piece of paper and you would punch holes in it and then feed it in. This was based on a jacquard loom, an mechanical weaving loom that was used in factories. And so that's what we used. And it had its biggest heyday in the early days of the 1900s, up until about 1960, when something happened to the mainframe and we started to create these decentralized terminals, later to be known as personal computers, as opposed to a mainframe that only had access by about 1,000 people. The PC opened computing to millions of people around the planet. And it was all thanks to this, it was made possible thanks to this breakthrough by Douglas Engelbart in the 70s. And he called it the mother of all demos. But what's most important in this demo was that he introduced something called a mouse, a computer mouse. And now we could point at things. Microsoft created MS-DOS, which is basically a coding language, but then the graphical user interface was developed by Xerox PARC, and it allowed lay people, like people that don't speak computer languages, to have control of the computer. It used images and text to create shortcuts. So you didn't have to write all the code. You can just push the little icon of the save or push the little, scissor icon and cut something, whatever, instead of having to write a string of code. So that happened. Xerox PARC introduced that in 1973 on something called the Alto, and then it was stolen or borrowed or commercialized, however you want to say it, by Steve Jobs in '84. Now, why are we talking about this? Well, it was designed to deal with this kind of software, right? And so it borrowed from the mechanical typewriter and a piece of paper to allow you to basically type text, right, with WordPerfect, or operate CAD, which was a very complex task. Either way, it was best done while seated. But since that time, all kinds of tasks have merged into that interface. So things that had their own individual, let's say, human-machine interface, such as a clock or a book, or a pair of scissors, or money. All of these things that had their own interaction metaphors are now all being pushed through this graphical user interface that was designed for typing on pieces of paper. And what we're seeing is that this is causing some significant problems in the way that we access these tools. We also see that there's a massive decline happening in PC over the past couple decades. And in fact, what we're seeing is that the PC is being replaced by the phone. And a lot of people think of this as the next paradigm of computing is the smartphone. But I'm here to tell you that actually that's not true. The smartphone is really just an extension of the PC. It's just that it's a much more portable version of the PC with smaller amounts of compute. In fact, the smartphone that I have today has more compute power than my first computer back in the 80s, right? And it's just that we now move the compute around with us in an attempt to fix the problems that we are having. But regardless, it still requires advanced function, advanced knowledge, specialized knowledge in order to achieve things like to create AI, for example. And of the world's population, this number is incorrect, I found out, it's actually 80 million people. Still, I know, makes a big difference in your opinion here, but there's 7.5 billion people in the world and only 80 million coders on the planet. That means 80 million people know how to write software that can be used to control all the objects in the world. That's a very small portion of the population that's able to do that. And if we look at that, 95% of the 80 million coders are male, and they live in quote unquote developed countries. But there's 4.5 billion people that live below the poverty line and 6-point-something billion people that don't have regular access to compute power. That's a problem, because cognitive computing no longer needs humans to encode data, right? It encodes its own data. It's capable of writing its own software, and we're developing tools every day that enable this type of thing. And it can make decisions faster than our own human perception. This example is pretty interesting. This is the Tesla drive assist tool. Never leave it alone without paying attention, or you could really end up in trouble. But I want you to pay attention to when you hear the audible beep happening from the car. That's a notification from the car that an accident is about to happen. Let's take a look. All right, let's watch that again. What you'll see is that that beep happens before the accident happens. And that beep is when the car starts to take evasive action, unlike the human that has to wait for the car accident to happen before it takes evasive action. So let's watch again. All right, so it was already starting to evade the accident before the accident even happened. So obviously, we no longer need to optimize no longer need an interface optimized for encoding data or operating software, right? We need to be able to augment human intelligence with these tools. And so instead, we need a technology. So we have a technology that can think on its own. Now we need an HMI that allows us to collaborate with that technology at the speed of thought. And so there's a lot of research going into this. This is a hint towards where the future of this is going. This is an EEG cap placed on the head of this woman as she trains a robot to sort paint. Now, you might think that she could just kind of say these things, but she can actually think about the fact that the robot's making a mistake faster than her voice can process it out. So the EEG cap basically detects when she thinks the robot's making a mistake, and the robot corrects its speed faster than the human being could get out of her mouth, you're doing it wrong. So by the time she thinks it's doing it wrong, it's already corrected course and done the correct action. Okay, now, I don't know about you, but I'm not putting that hat on. I have great hair, and I'm not want to wear that thing. So we need to come up, oh, well, Nikki might want to wear that thing. We need to come up with a new way of doing these things, right? A lot of people think, oh, okay, well, speech. Speech is the solution. No, it's not. Speech is not an actual native to your brain. It's a second order of activity. It requires conscious thought to develop words, even if you don't realize it. And even still, you know, while we can only type at 38 words per minute on a smartphone, and 52 words per minute on a keyboard, we still only talk at 150 words per minute. And thought, like your linguistic thought, is only 400 words per minute. That's still too slow to keep up with the pace of cognitive compute. We need to see something that can achieve the speeds our brain is doing. Now, you may have heard before that you only use a certain percentage of your brain. That's just not correct. You're using all of your brain all the time. It's just that most of it is not conscious activity. You don't actually understand, you're not conscious of what's happening. And even though we aren't fully aware of how it all does what it does, we do know that humans already have an interface to the world. It's called human perception. And this is a great book if you're interested in this topic, The Case Against Reality. And basically what we know is that humans actually have limited perceptual range. But that perceptual range has been evolved over time to help us to survive in the environment we live in. And the brain has developed certain areas of itself to take in the sensory information about the world around it, to process it, and to trigger some of the innate background activity happening. So the brain actually uses senses and movement to help us to process the world around us. In fact, we have embodiment of our brain. It's our mind. It's not something that just sits in our brain and tells our body what to do. We think with our entire body. We see this when we look at, say, emotion. Emotion is felt not up here, but throughout the body. And when we look at the blood flow, when people are experiencing these emotions, we see that the blood moves through those areas of the body where you're experiencing the emotion. So you're actually embodying that experience, and you're thinking with your entire body in all sorts of ways. Let's look at walking, for example. Walking is not something you're paying attention to. It's just happening in the background. It's more like controlled falling when we look at how much thought it requires, right? So there's a not quite random pattern that happens to your steps. The last 10 steps are related to the next 10 steps, but the next 10 steps after there have very little to do with the original 10 steps, and so on and so forth. It's a constant creative act. And when we look at how the brain manages it, it sends most of your tactile receptors to your feet, so you can almost feel in front of where your foot is stepping. This is why when you stub your toe while walking, it hurts like hell. But when you bump your toe while sleeping or laying down, it doesn't have the same effect, right? So the brain is actively paying attention to different sensory activity and movements and things without requiring any thought from your short-term task-based memory. Okay, that's how the brain works. And in fact, when you engage more of the body and the senses, you become better, more effective at thinking. Geez, we only have 19 minutes left. Okay. So the way that we improve human performance is through ergonomics, right? Ergonomics amplifies the output of a human in a physical system, right? So we looked at this in terms of skating, but now let's look at it in terms of technology. So we already have wearable robots such as this one from Exobionics being used in in industry. So this is a robot from some good friends of mine, and they have created this robotic exoskeleton for frontline workers at Ford Motor Company that are working on the chassis all day long. So their hands are above their head all day long with heavy tools. Now, this means that most of those workers, there's a lot of injuries on this job. They have short careers because of all the wear and tear on the body. And unfortunately, that's not a job a lot of people are eager to take on right now. So it's causing a problem. These robotic exoskeletons allow the chassis worker to keep their hands above their head all day long without any effort on the part of the human being. It's like a prop. And this is extending the lifetime of people working on this job, and as well as dramatically reducing the injuries. And that's just like a little switch to the ergonomics through technology. We also have things like this wearable robot from GM. Now, instead of teaching their frontline workers how to write computer code in order to control robotics, what they did was they just put the robot on top of the human hand. So to control the robotic hand, all I do is this. And now I lift 10 to 15 kilograms with the amount of effort it takes me to lift 5 to 10, right? And I do it all day long. I never get tired. It's pretty remarkable glove. All right, so we can amplify physical power. Cool, through physical ergonomics. Let me introduce you to a new concept. Cognitive ergonomics. Cognitive ergonomics do basically the same thing to amplify human cognitive output. All that it does is similar to the physical. It reduces the steps necessary to complete tasks by leveraging existing cognitive functions to amplifying their output. Really simple, basic example of this is multi-monitor situations. Space improves productivity, especially in multitasking situations. So just by using space to offload tasks to different monitors so that you can move between them simply by moving your head and not through that interrupting interface doorway, you become 40% more productive. This is using your innate cognitive function called spatial cognition. Your brain is constantly creating a map already. So if we can just leverage that for technological tasks, we dramatically improve the functionality. Basically, we're just using the existing way the brain works to reduce the number of steps between intent and completion. We can get fancy with it. We can hijack your senses directly and provide synthetic feed of those senses to the brain, such as with vision. Vision's important. It's the most important sense you have. It takes up about, it's what you use to triangulate all of your other senses. It's a huge portion of your brain, and it's inherent in nearly 85% of your cognitive abilities. Virtual reality hijacks it by taking the screen from across the room and shoving it up across your face. Now your brain can't differentiate between what it's seeing and all the other senses, which is why you fall over and you're terrified to step off that plank, if you've ever done the walk the plank example. It's so powerful that it can transcend pain. So our brain believes it so fully that they'll believe it over anything, such as this example. This is a research done by the University of Washington's HIT lab. And what they were doing is they were helping burn patients who had burns over 85% of their body. Morphine reduced their pain by 20%. So these researchers created this game that allowed the patients to be immersed in this icy wonderland. And the first thing that happens is the brain says that burning sensation I'm experiencing must actually be cold. It's not burning, it's freezing. I'm freezing. Then on top of it, we're distracting them by having them throw snowballs at these penguins and snowmen. And the brain forgets about what's happening on the outside for a minute. This game can reduce pain anywhere from 50 to 65% versus morphine's 20. And better than opioids, it trains the brain to be able to sum up this visualization whenever it's needed. So they don't have to become dependent on this VR visualization. It trains the brain how to pull it up at any time. And so it's less dependent and more empowering of the human. This direct feed can be used to rehydrate something called neuroplasticity, or the brain's ability to wire itself. So they used to think at age 12 that ended and there's nothing you could do about it. But my friend James Blaha had something called the lazy eye, meaning his brain has stopped paying attention to his eyeball. The neural connection was no longer active. So what he did was he used this VR tool to create a little bit of data, create this game called Vivid Vision that you can download if you know somebody who has diplopia or any other treatment like that. And it's sending one piece of data to one eye and a slightly different to the other. And this caused the brain to start to pay attention to the lazy eye and recreate a neural connection to this. Sorry, I'm just gonna, just for sake of time, how many of you have actually seen me talk before and know all this stuff that I'm about to say? Marcus, Michaela, I'm imagining, no, and Nikki. Okay, just want to make sure, see, I don't want to recover things that I've already said before. All right, so what's important is that James, after playing this game, what happened is that the brain started to pay attention again to the lazy eye. So the eye that's not, that was just kind of drifting in its socket. And within a month, he had rehydrated, he had fixed his vision in the virtual space. So he could see in full 3-dimensional, meaning that his lazy eye was back on board and he had both stereo vision now. And when he took the headset off, he had fixed his lazy eye entirely. So while medical intervention couldn't help it, such as medication or surgery, this tool basically created a new neural pathway between the brain and the eye. This is remarkable because it can be used in fascinating ways. So there's this law when it comes to the brain and how we put together information called Hebe's law. And basically it says that the neurons that fire together wire together, meaning that our brain starts to hard code certain patterns into what we call chunks of information, right? So the more expert you become at some area, the more chunks you have that shortcut the knowledge that you need to do it. It's kind of like, basically like what GUI did. It's creating these like little chunks of code that the brain just fires off all at once instead of having to think through all the different things that need to be fired. Basically the same thing as an icon, but for the brain. Now, how this plays out is evident in something called the Walk Again project from Duke University, and a guy called Dr. Nikolai. Now, what they did is they selected 8 paraplegics, people who had some sort of damage to their spinal cord that stopped their ability to walk. And they put that scary looking hat that Nikki wants to wear on these people, and they put sensors all over the hat. Now the one in red there is on the primary motor cortex, also known as the M1 neuron. The M1 neuron basically runs from ear to ear. And there's different parts of the neuron that are dedicated to movements of the different parts of your body, you know, from like your eyelids to your toes to everything in between, right? Now they put a sensor right here, which is where your legs are basically. And they train the paraplegics to be able to control a pair of avatar legs to walk. And once they got good at that, they also added a pair of robotic legs. So now the brain is seeing it, and also movement, the kinesthetic knowledge is there. And so what happens is that not only does the neuroplasticity from the eyes, but then we also have new neuroplasticity to the legs, and it's starting to create these chunks in the brain that allow the body to recreate the musculature and circulatory system necessary to walk again. And then after about a year, these chunks become so embedded that it creates a whole new neural pathway from the brain to the legs to allow voluntary leg movement. Now, this is impressive because what's happened is that basically the brain has taken in the synthetic movement and visual stuff and created these chunks of neurons that fired together that made the brain believe the body could walk. And then that created a new neural pathway between the leg and the brain to enable these folks to walk again. Now, you might be asking me, why are there so many medical examples? Well, one is cost. Back in 1993, when Snow World came out, this was the state of the art of VR technology. It cost $70,000. And I specialize in this technology. There's no way, I couldn't even set this up. Nope, couldn't do it. Today, you can buy a much superior headset for $399 that doesn't have tethers. It's basically plug and play. And so now we're running software on hardware. And we know how to make software. Software is easy. The hardware is the hard part. So today we have massive studies going on around pharma VR for everything from anxiety, depression, pain, but also things like Alzheimer's, MS, you name it, we're attempting to create these tools. The other thing is that as we approach this human interface to the world and try to create tools that interact with it, we have to recognize that one size doesn't fit all. When it comes to brains, there's a wide array of neural diversity, right? So each of us on this call have different special parts of our brain. Some of us might have a little bit of dyslexia. Some of us might have sound sensitivity, whatever. We have a neural diversity. And so we have to create tools that work for way more people. It also means that we need medical access to get to people that have special needs so that we can learn about how we can leverage those tools to change interface. And this is really important because people in the system normally can't see outside the system. One of my favorite quotes from Marshall McLuhan is that we shape our tools and forever our tools shape us. And that's especially true when we look at the interface that we have today. Most of us don't even realize the problems with interface. But even bigger, when it comes to the human perception of the real world, most of us would say that we see everything in the real world. We can see all the things. But we know for a fact that that's not true. My dog, he sees and smells, he's blind, but he navigates way better than he did now than he did when he was sighted, because it's only through smell that he's navigating. This is true about something called touch, right? So if you think about touch, you don't really think about it too much during your day. It doesn't seem to affect you that much, right? It's just I can touch something, great, I can feel it. But in fact, touch is your first sense to develop. And you develop it right away. You discover that things that are hard are bad, and things that are soft are nice and warm and welcoming. Now, you probably don't realize, but that affects you your entire life. Not in a conscious way, in a subconscious way, in that background processing sort of way. If you're seated in a nice, comfy chair right now, you're more likely to believe what I'm saying. If you're sitting in a hard chair, you're much more likely to doubt every word that's coming out of my mouth. Numerous studies have proved this time and time again, that the surface that you're sitting on affects the way that you see the world around you. Now, we are not necessarily articulated about this because most of the people on this phone call can see, and we rely on vision as the primary sense. But blind people think about it all the time. Blind people use touch to navigate the world in the same way that you and I use sight. And when I first started working on tactile interface called haptics, I was lucky enough to collaborate with a man named Noel Runyon, who was blinded at age 17 when a press exploded in his face, an ink press exploded in his face. Yet he still managed to work for some of the first UI for IBM. Okay. So Noel helped me to understand how blind people use touch to navigate the world. And that, of course, led to really interesting experiments. And this is happening all over the world. So YCAB is a really interesting company. They're helping blind people to see again through something called the brain port. And what you're seeing here is a camera is focused on the front of this pair of glasses that's translating the world into a 100 by 100 pixel haptic grid, which is basically what you see here, this white tablet. That's a vibrotactile tablet that she's going to put on her tongue. And what happens is that the camera translates the picture into a 100 by 100 pixel grid that basically would look like this, but it's being broadcast through that vibration. And with it, blind people say they can taste sight. So this man, he's able to read, he's able to see his daughter's face and tell the difference between her face and some random stranger. He can play football. He can do all kinds of things with this tool. It's like the cochlear implant for blind people. Now, as I mentioned, we have limited visual range. And in fact, we know that, say, dogs see in sight and that dolphins communicate in sonar. For sake of brevity, I'm going to say go check out speakdolphin.com because I'm going to move on. We can actually create new senses for human beings, more perceptual range for human beings. There's a great guy named Liviu who owns a company called Cyborg Ness, who did this crazy experiment where he put a vibrotactile sensor in his chest that always vibrates when he points true north, much like birds. While this might seem kind of crazy to you, it's very effective for people that are navigators, pilots, military folk, and so on. There's also people like Neil Harbison, who worked with our friend Adam Montadon to create this little device that allows this colorblind artist to hear colors directly to his brain. And his partner, Moon Rebus, has a sensor in her feet that allows her to feel and anticipate earthquakes before they happen. So great. So we can create all new sensory interface. We can amplify human capabilities. It's going to be shocking what we can do. But if you're like me, you might be saying, wait, won't that create a greater divide between the haves and the have-nots? Won't we have superhumans and like normal everyday humans living in poverty? Well, maybe. Except for that, if you look at the way that this kind of disruption happens, today's hardware technology companies are chasing this high end of the market. So they're creating even more specialized tools, more complicated tools, tools that require specialized knowledge. And look at this big, ginormous gap that is just waiting for a disruption. Disruptions happen at the low end of the market for people that are outside of the existing systems, people who don't necessarily have the money to pay for these high-end tools. And I'm going to go back to here. That 80 million, not 18, out of 7.3 billion, this is the people with the most amount of technological power. And this is the amount of people at that high end of the market there. Look at this ginormous swath of the population that's missing out. If we could create a solution for this 6.3 billion, we'd have somewhere around a $7 billion market. So allow me to introduce you to IoT. IoT is disrupting the form factor of compute. So instead of it being decentralized, right, as we see in the PC, now it's also distributed to the edge of where compute happens. And this is on its own exponential pace. So in 2014, you could get this little tiny chip that fits on an eye of a golf ball for 75 cents, which has led to the IoT market. But today, that thing is as functional as my first computer back in the 80s, and it's still that tiny little chip. The price is dropping on all kinds of sensors, which is leading to this sort of edge computing where we put AI right on the edge in these little tiny chips. And on top of it, we're creating software, not hardware, which drops the price dramatically again. All this is leading to people without any technological knowledge being able to create really powerful cognitive computing platforms so that a farmer in sub-Saharan Africa is able to string together some of these things to create a tool that helps her to address the pestilence and famine and all these other cycles that happen to these crops in a very powerful way. So suddenly we have a world of superhumans. Or we can continue to make supercomputers for that small little 1 billion population. Personally, I choose to make tools for humans. You? Thanks.